So my talk from Bright Photonics will be focused on development of custom photonic integrated circuits for data centers. Here I would like to put special attention to technology selection, design, and validation, and also criteria underneath that. Just a few words, introduction on Bright Photonics and what we are doing in general, but also later on within the MASSTART project. So at Design House, we empower products with photonics engineering. We focus on prototyping, supply chain development, PIC design, and IP blocks development. You may know that the product is composed of many other aspects, not only photonics, but also electronics, control, mechanics, and materials. At Bright, we are very much focused into one of those circles, which is photonics. And for that, we design from ultraviolet to infrared, many different photonic integrated circuits across technology platform, and also we focus on design flow innovation. But just to focus more into the MASSTART project and Data Center Interconnects, we will be looking here into a closer space, which is mostly related to O-band and also C-band applications, depending whether we are considering inter or intra data center communication. Within the MASSTART project, just to give you some background on that one, we have a number of industrial and academic partners that focus on mass manufacturing of transceivers for terabit per second application and for terabit per second era. And here in our consortium, we have both technology and equipment providers. You will hear from them, and this is Leti, Team Photonics, Fraunhofer, Almae, Tektronix, and Ficontech. We have also support in the middle application layer for design and technology consultancy. That's Bright Photonics, Fraunhofer, and Aristotle University in Thessaloniki. And on top of that, we have the system providers and application users like ADVA, Mellanox, and now NVIDIA and Dust Photonics. So as a design house, we will focus on the middle layer, which is related to design and the design technology selection. Just to give you also a brief background on why we are with MASSTART at this point of transceiver development for terabit inter and intra data center application, we actually started within the European support a number of projects that were predecessors to this development related to optical interconnection and 3D integration technology. That was within the Foxtrot projects, where we are focusing on 400 gigabit per second application. Then we moved into the L3 matrix to develop co-packaged technology platform for switching and transceivers to reach the terabit per second application. And now we're going beyond that with wavelength division multiplexing for inter and inter data center chips. And that part at Bright will be very much focused on design aspects of those components, which are optical interconnects, IP blocks, and photonic IC concepts, integration technologies, so their selection and proper choice for the application, and also PIC layout design, which is photonic integrated circuit layout design, its validation, development of the tooling and ways to perform design rule check, and also implementing photonics design kits. So all the users later on, as part of exploitation of this project, will be able to join the technology run from our technology providers and design their components and design their photonic integrated circuits. So just to give you a flavor of those 4 points related to the development aspects, I will share some examples with you with this presentation. So in terms of the optical interconnects, where is the current development ongoing? It's of course in having different modules interconnected with each other, either at the chip-to-chip level using, for example, vertical couplers or adiabatic couplers, either chip to a board or board-to-board interconnects. So that are different types of optical integration and optical integration schemes that can compose either edge couplers or grating couplers that were mostly subject of development in the previous project, which was called L3 matrix. And with the MASSTART project, what we do, we focus mostly on the edge coupler development, how to interconnect different material technology platform, and how to efficiently couple laser and laser arrays between different circuits. And for that, we use Sealeti platform and Team Photonics with mode converters realized on their glass interposer chips. Another very important part for developing your custom photonic integrated circuits is to use optical engines. And those optical engines are typically IP blocks or complete photonic integrated circuits in the form of, for example, MAX or DMAX components, lasers, both in O-band and C-band, various spot size converters or interconnects itself, and for example, polarization handling devices. And within MASSTART projects, we very much focus on different type of component development, and you will hear on that one more specifically from technology providers. Having those custom optical engines, you can form more advanced photonic integrated circuits. And here is an example of a switching matrix that we developed within one of the projects where we compose those IP blocks from different users to form more advanced engine, for example, for switching purposes in data centers. What is also very important while developing your custom photonic integrated circuits is to consider different technology aspects and different material platforms. And for that, we typically go into analysis of the material capabilities and how to combine passive components. Typically, we would like to have a low loss passive components and the active elements like lasers. So you might be familiar with different material platforms like silicon-based, silicon nitride, indium phosphide, lithium niobate, or polymer that can be used to develop certain functionality on the platform. But for some of the options, and these are also options that we investigate within the MASSTART projects, is how to, in the efficient way, combine 3-5 components, which are lasers with silicon technology platforms. And here you can see some of the examples of that type of integration. So you can either use lensed coupling between the active component and the passive component. You can use edge couplers, you can use vertical couplers, and there are other ways to do it as well, either via wafer die bonding or heteroepitaxy. So there are now numerous ways to do this development. And when you think more likely into transceivers and how to realize those, you have to think of combining indium phosphide and silicon platform. So if you would be choosing, for example, indium phosphide as your main integration platform, you probably can integrate most of the optical components like lasers, modulators, coherent receivers. However, the drivers and TIAs, as well as the DSP, those would have to migrate into different technology like silicon, germanium, on CMOS. For the transceivers that will be formed within silicon-based platforms, you probably can integrate most of electronics, modulator, or coherent driver of silicon and CMOS-based technology. However, for laser itself, you would need to choose one of the available integration forms, as mentioned previously on the slide. So lensed coupling, edge coupling, or other ways of bonding 3-5 into silicon to obtain most of the integration and performance. And if we will be looking into comparison of different technology platforms like indium phosphide, silicon photonics, and the way of combining indium phosphide with silicon, we would have to take into consideration both technical, production, and economic and supply chain aspects. So for each application, we would need to analyze into and take into account options like optical loss, coupling efficiency, availability of different components like photodiodes, MAX, DMAX, polarization control devices, or electronics. From production perspective, we will be looking at the costs of them, on the need for different substrates or substrate regrowth, like in the form of 3-5 materials, using or not silicon or silicon substrates, and what would be our overall yield and footprint of the devices to form or to fit in our certain form factor in the data center or other environment. And of course, what is also important is the cost of this development, both the substrate cost, but what sometimes is omitted are the assembly and packaging costs, testing itself, and wafer size, as well as scalability. And what is most suitable to your technology typically or always depends on the application and specification. volume available or proven yield at the foundry, as well as costs of development and access to the foundry facilities for your product development. And what we also see in the development of custom photonic integrated circuits, it's moving towards complex and modular system where we reuse the chiplets on different material platforms. We reuse the IP blocks and circuit blocks to form photonic-based applications. And that probably can get us way beyond 50 terabits per second if we will be thinking of increasing the wavelength multiplexing, polarization multiplexing, parallelizing different lanes, and using more advanced modulation scheme like 16 QAM. What is also important in the development of the photonic integrated circuits is the design aspect of that one. And within the MASSTART project, we use Nazca-Design, which is photonic IC design framework based on Python, where we implemented foundry PDKs as well as information about the package and assembly requirements from our project partners. And using that tool, we are able to combine multiple technologies to design photonic integrated circuits. We develop PDKs that define the very specific technology informations like the layers and the material properties. We are able to exchange between the partners IP building blocks, which are IP protected building blocks. We can combine them to create new components, new libraries. And we also facilitate here scaling and proper accuracy of the GDS and of the mask information in that project. We saw here different routing and design rule checking aspects with that tooling. I will show some of the examples later on. And we also facilitate here information on assembly, coupling, and packaging approaches by adding appropriate fiducials, electronic information into our design flow. So having all those information in the PDK, in assembly design kit, we are able to produce the designs for our application users like NVIDIA, Mellanox, and ADVA. I also mentioned that it is very important to have a proper design validation in GDS, and we have also developed that and are using within the MASSTART project. Here is just an example of a simple switch combined with the max and dmax. So what we do with that design, we are able to have a very accurate path tracing, path counting of the signal going through the device at the GDS level. We are able to check on different type of connectivity and whether there are whether there are mistakes in that, either at the cross-section level, visualize it properly at the GDS, but also in the logging information, check the width aspect, check the unappropriate angles as well as gaps within our circuit that might happen if the components are not correctly connected. On top of that, we also added simulation and verification at the GDS level to be sure that what we send to the foundry is actually simulated at the layout physical level. And here, using the MASSTART examples like ring filters, hybrid 90, we are able to investigate different characteristics of our circuit, like transmission, or extract S matrices and further on analyze the performance of our circuits. And to show you some of the examples of what we have tape out within MASSTARTs for inter and intra data center peaks using the Leti and team PDKs, you can see some of the screenshots of the layouts as well as actually fabricated chip for that project that is now currently being tested by the application users. And with that last view on the chips that we have, I would like to thank you for your attention. If you have any questions related to the MASSTART project, feel free to contact us either for the supply chain, peak concept, IP blocks, prototyping, or PDKs, and get access to the technology. Just feel free to contact either MASSTART or bright photonics. Thank you very much.
Thank you very much, Katarzyna. I don't see any questions in the chat window yet. So if you have any questions, feel free to post them. In the meantime, maybe let me ask one question. In the past years, have you seen any evolution in the approach to PIC design? I assume PICs have gotten more complex over the years, so probably you need better tools for, let's say, first of all, design, but also LVS and DRC. What's the major progress in the last couple of years in that area?
So yes, indeed. I think mostly what we observe now in terms of more complex photonic integrated circuits development is to combine both electronic components and photonic components together, both at design level and also try to have it at the simulation level. So that's one of the improvements that is going on. And also from our own perspective, we also see that the electronic design flow is different from the photonics design flow. In the sense that typically in photonics, people start from designing a layout rather than analyzing the schematic. This is because the photonic circuits are still much simpler than electronic integrated circuits. And to facilitate that design flow, which we also internally quite often follow, we actually introduce the simulation at the GDS level. So we extract the information from the GDS and simulate actual GDS to make sure that what is in the layout, what are the physical dimensions on the chip, these are actually simulated. And this is the way we try to go now to skip the step layout versus schematic and do schematic as a layout itself. Typically also because the optical information not always can be precisely kept at the simulation level, but has to be